Hello everyone, welcome to our YouTube channel Electronics Maddie. In this video, I am going to demonstrate closed loop simulation of SEPIC Converter in MATLAB. In case you haven't subscribed to our channel, please do subscribe to it, only then you'll get the videos that we post regularly. Alright, let's get started. This is the circuit diagram of a SEPIC Converter in closed loop mode. This is basically the MATLAB model that we're going to do. So just to give you an overview, I've just added up this in this particular place. So take a screenshot of it, take this as reference and we'll start building the circuit in MATLAB. So with respect to design of SEPIC converter and open loop operation, I've already made a video and the link will be provided in the description and it will always be available in the end screen as well. So please do watch it in case you have not watched it. However, we'll be building the closed loop model from the scratch, but just with respect to the design perspective, that video will really be helpful for you. In MATLAB, we'll be clicking on Simulink library browser. So we'll be searching the components that we want over here. At the first place, we'll be requiring a PowerQ block, which is essential for the simulation to take place. So search for PowerQ. We'll be requiring a voltage measurement block as well. So add that. And once these two are added, we'll be using a DC voltage source. So this is the one that we'll be adding. So choose the ones that are there in black because the ones that are there in blue are used for signals and systems application and digital signal processing application. Once this is done, we'll be using a series RLC branch, so we can later convert it to the type of circuit that we want, whether a resistor, inductor, or capacitor based on our requirement. We'll be using MOSFET as a switch. We're not going to use thyristor because we need an external commutation circuit. However, we can use IGBT as well. Nevertheless, it doesn't matter. So we will be requiring a diode as well. So search for diode. You'll be getting it right at the bottom. Scroll down and add that block as well. Once we've added all of these, we'll be requiring a scope in order to see how the waveform looks like at the output. So search for scope, you'll be getting right at the top. Once we've added all of these, we'll start off with respect to the closed loop model. We'll be requiring a constant block, which is basically the reference value that we set up, and add that block. And we'll be requiring a difference block. So search for sum. You'll be getting both sum, difference, subtract, all the operations over here. So add subtract operation, and once this is done, we'll be requiring a PID controller. So search for controller, you'll be getting PID. Choose the ones that is there in with respect to S domain, and we'll be adding that block. Once that is also added, we'll be requiring an ABS block. So search for ABS block, and it will be available over here. This is used in order to obtain the absolute value of a particular signal. So the output of the PID controller, only the absolute value will be taken, and it will be compared with a repeating sequence. So we will be using a repeating sequence. Search for repeating sequence and then add that block. So over here we'll give this switching frequency with respect to a circuit, and that will be compared with respect to the absolute value of the output from the PID controller. So once that is done, we'll be using a relational operator in order to compare these two signals at the closed loop end, and we will be giving the output to the gate terminals. So we have added all the blocks. So what we'll be doing is we'll be placing them in appropriate positions, and then we can get started with the circuit and enter our parameters. All right, here we are. So we'll be entering our supply voltage, and the value of supply voltage is chosen to be equal to 15 volt. Connect it to this, and we'll be changing. Double click on this, and we'll be choosing an inductor over here. Choose the value of the inductor L1 to be equal to 35.62 microhenry. So enter E into 10 power minus 6 over here, and this is according to our design procedure. And once this is done, we'll be connecting it in this particular fashion. Double click on this and disable the measurement port with respect to both MOSFET and the diode that is used in our circuit. So once that is done, we'll be connecting it in this particular fashion, and we'll be requiring a capacitor. So Control C, Control V. Later on, we can change it to be a capacitor, and its value is chosen to be equal to 28.57 microfarad. So 28.57 is the value that we are going to enter. And once that is done, click on OK, and we'll be connecting in this particular fashion according to our circuit. Rotate this, and we'll be using another inductor, and its value is chosen to be equal to 14.25 microhenry. So we'll be entering 14.25. So once this is done, the value of L2 is entered. We'll be connecting the circuit in this particular fashion, and we'll be connecting the diode over here. We need another capacitor, so we will be copy pasting this and rotate it in this particular fashion, and its value is the same, that is with respect to C1, so we don't have to change anything over there. Control C and Control V, will be using a resistor. So change the value of resistance to be equal to 2 ohms and connect it in this particular fashion. So once all of these are done, we'll be measuring the voltage across the resistive load in this fashion, and we'll be giving it to the scope. So we will be taking the tapping from the scope over here in this particular fashion, and the reference value, we want an output voltage of 6 volt. Whatever output we want, enter it over here. So that will be compared with respect to our actual output voltage, and it will be given to the PID controller. So we'll be using an integral controller over here. It basically depends on whatever approach that you use. So I'll only be requiring an integral controller, and its value is designed to be equal to 7. So enter that value, and you can change. This keeps changing according to your requirements. Based on transfer function approach, you'll be designing it. It will be given to the absolute value of a signal, and it will be connected in this particular. Once that is done, we'll be entering the values with respect to the repeating sequence. So the value that we have chosen is 1 by, with respect to 25 kilohertz, if you're doing 1 by 25,000, and the output value is with respect to 1. So enter that, and that will be given to the gate terminals in this particular fashion. Greater than or equal to will compare these two signals and will produce the output. Set the simulation time to be equal to 0.5 seconds, and then we can click on run to check how the output waveform varies. So we are supposed to get an output voltage of about 6 volt with respect to the input that we have given and with respect to our design parameters. So let us see. It does take some time for the simulation to take place, so be a little patient. Alright, now let us look at the waveform by double clicking on the scope. So if you carefully observe, we are getting with an average value of about 6 volt at the output. So however, the ripple is very high, so we can further reduce it by choosing suitable value of capacitances and inductances. So if you see, however, the average value is 6, and that is what we want. So now how do we justify this? This is the closed loop operation. So that is one of the important aspects that we have to think about. So let us say I am changing my supply voltage, say equal to 20 volt. So what happens in open loop? The output voltage also changes because supply is changed. But in case of closed loop, that is not supposed to happen. You should still be getting 6 volt irrespective of the changes in the supply. And if that is possible, then we can definitely say this is closed loop operation. So we'll click on run and check how the waveform is. So in case of open loop system, when the input changes correspondingly, the output will also change. But in case of closed loop system, the output should still remain the same with the changes in the input, and that will justify that this is a closed loop model. And that is why closed loop is more effective with respect to open loop. So we'll double click on the scope, and we will be restoring it to the original view. If you see the output, it takes some time to settle, and the output is still 6 volt. How do we say that it is still 6 volt? If you zoom in a particular portion, so if you see, the ripple is still the average value of the signal. If you see, the ripples are very high, but as a whole, if you see, the average output voltage will still be remaining at 6 volt. So in case you use a display block in order to see how the voltage varies, so this is how the signal is. The ripples are very high, but you can further reduce it, but the average output voltage will still be equal to 6 volt if you measure. So this is how we will be justifying it. You can try it for different input values, but however, there will be a certain tolerance. You cannot randomly take 100 volt at the input and see what is the output. You have to get 6 volt. That is not practically possible. So only with respect to a certain tolerance limit, this is possible. So based on that, we will be designing our circuits as well. I hope the simulation of this particular circuit in closed loop model is understood. So in case you have any questions, feel free to reach out. If you like this video, please do like it, share it, and subscribe to our channel for regular updates. Thanks.